Hello. So for this video, we're going to be working on part B of the linear momentum problem. Part A was in the previous video, and in this video, we're going to try to find the magnitude and the direction of the change in the truck's momentum. So what we want to find is the change in the object's momentum, and then we want to take the magnitude of that. So the magnitude of the change in the object's momentum. So we know that change in momentum is going to be the object's final momentum minus the object's initial momentum, right? And so we also want to take the magnitude of that. And we know that momentum is equal to mass times velocity, right? The object's mass times the object's velocity. So the final momentum, therefore, is going to be the object's mass times its final velocity. And we want to draw a vector on top because momentum takes into account not only the magnitude of the object's velocity, but also the direction of its velocity. And then we want to subtract the initial momentum, which is going to be the object's mass times its initial velocity. And we want to take the absolute value of that because we're looking for a magnitude. So in this case, we can factor out an m from both terms on the inside of the absolute value signs based on the distributive property of multiplication. So now we want to get the absolute value of the mass of the truck times the difference of two vectors here, final velocity and initial velocity. So we can say that the final velocity minus the initial velocity, we can call that delta V. Right, we can call this difference of two vectors delta V, right? Because delta just means the final of something minus the initial of something. So in this case, let's draw a diagram of the truck's motion. So first, we have the truck moving north at 41 kilometers per hour. And in the previous video, we converted kilometers per hour into meters per second. So in this case, if we convert it to meters per second, we get 11.39 meters per second. All right, so that's the velocity of the truck's initial motion. So, and we know that it's going north at this point in time, right? Because the problem mentions that the truck is traveling north. So we want to make sure that this arrow is pointing upwards or in the north direction. And then we know that the truck turns east and then accelerates or goes faster, and then it reaches a speed of 51 kilometers per hour. So let's go ahead and draw another vector here in blue going east or to the right. And let's make this vector a little bit bigger than the first vector because it's going a little bit faster. And then if we convert kilometers per hour into meters per second, 51 kilometers per hour translates roughly into 14.3 14.17 meters per second. And this is going east or to the right. So now that we have a diagram of the object's motion, we want to subtract the initial velocity from the final velocity, right? We want to find delta V, which is final velocity minus initial velocity. So incidentally, VF minus VI is the exact same as VF plus negative VI. Right? Subtracting VI has the same effect of adding negative VI. So, and this is because the negative of a vector has the same magnitude as that vector, but has an opposite direction. So, all we're doing is taking VI and then pointing it in the opposite direction. Right? So, instead of east or to the right, we're going to be pointing it in the opposite direction, which is to the left or west. So now let's add these two vectors. When adding two vectors, you draw the first vector, connect the tail of the second vector to the head of the first vector, and then you connect the tail of the first to the head of the second, and then draw a vector connecting those two. So let me explain. So first, let's draw VF. So VF was 14.17 meters per second to the east. So let's draw that vector right now. Here's VF. And now let's draw negative VI, which is VI in the opposite direction. So instead of pointing upward, we want to point it downwards. So in this case, we want to connect the tail of this new vector, negative VI, to the head of VF. So let's go ahead and do that now. So this is negative VI. And this vector up here is VF. Okay, perfect. So now we want to draw a vector from the tail of VF to the head of negative VI. So now let's call this new vector delta V. Let's draw it. Let's draw this vector in green. So from the tail of VF to the head of VI. And this is how you add two vectors together. So now the magnitude of the change in momentum will be the magnitude of delta V times the mass of the truck. And that's going to give us the magnitude of the change in momentum of the truck. So, and likewise, the direction that this vector, delta V, is pointing is going to give us the direction of the change in momentum, right? Because delta V tells us which way the change in momentum is happening. So now, let's try and find the magnitude of delta V. So if you remember, delta V is going to be the sum of two vectors, VF and negative VI. So we have to add these two up. We can do this by breaking each vector into its individual components and then adding up those components together. This sum or difference will be delta V. So let's go ahead and do that now. So since VF only extends in the x direction because it's traveling east or to the right, we only have an x component for VF. There's no y component to VF. It only travels upward. Sorry, it only travels to the right. It does not travel up. So we can say that VF one second. So we can say that VF is gonna be 14.17 I hat meters per second. And what I hat means is, so I hat is a unit vector that indicates the direction the vector is pointing. So I hat indicates that a vector is only projected along the x-axis. It's going to be the component of the vector projected along the x-axis. So in this case, because there's no y component of VF, there's only an x component of VF, this is going to be our vector VF. And let's do the same for negative VI as well. So negative VI is equal to negative 11.39 meters per second J hat. So J hat in this case is going to be the component of vector negative VI projected along the y-axis. Because the vector is pointing downwards, we use negative J hat, which means that it points in the negative y direction, or to the south. So in this case, now we can just add these two vectors up. So we know that delta V is equal to VF minus VI. And let's add a vector on top of this. Okay, perfect. So now we know that VF is equal to 14.17 I hat meters per second. And we know that negative VI is equal to negative 11.39 meters per second J hat. So this is going to be our vector, delta V. So to find the magnitude of this vector, delta V, we use this formula. Delta V or in this case, the magnitude of delta V, this vector right here, the length of this vector is equal to the square root of Vx squared plus Vy squared. So we want to take the square root of the sum of the squares of the x component of delta V and the y component of delta V. So we know that the x component of delta V is going to be the projection of delta V along the x-axis. So this portion right here of the vector. And we know that, so this is Vx. And we know that Vy is going to be the projection of delta V along the y-axis. And we know that Vx, the length of Vx, is going to be equal to the length of Vf, our final velocity. And we know that Vy is going to be equal to the length of negative Vy. Sorry, of negative Vi. So we can say that actually, let me sort of explain where this formula comes from first. So this formula comes from the fact that delta V, Vy, and Vx form a right triangle. And because these three vectors form a right triangle, we can use Pythagorean's theorem. And Pythagorean theorem states that a squared plus b squared equals c squared. So actually, so in this case, let's call a Vx, and let's call y Vy b, and let's call delta V c. So these are going to be the sides of our right triangle. So in this case, since a equals Vx, we can say Vx squared, and since Vy equals b, we can say Vy squared. And since c is going to be our hypotenuse, or rather the length of delta V, we can say that delta V squared is going to be equal to c squared. So to solve for the length of delta V, or the magnitude of delta V, we can square both sides of this equation and therefore get delta V, rather the magnitude of delta V by itself. So therefore, delta V is equal to Vx squared plus Vy squared. And so this is where we get this formula from. So now we can plug in our components into the formula and then get the length of delta V. So since Vx is equal to the length of Vf, which is over here, we can say that Vx is equal to 14.17 meters per second squared. And since Vy is equal to the length of this vector here, negative Vi, we can say that Vy squared is equal to negative 11.39 meters per second squared. And let's take the square root of this whole entire thing. So actually, I think this vector should be pointing downwards instead. So ignore this part. So this vector should have a downward trajectory. So now let's solve for what's on the inside of the square root sign. So when you square both terms and add them together, you should get 330.5 meters squared per second squared. And then we can square all the terms on the inside, meaning we can square the 330.5, the meters per second squared, and the meter squared and the second squared. And then we should get 18.18 meters per second. So this is going to be the magnitude of the change in the object's velocity. So now, to find the change, or rather the magnitude of the change in the truck's momentum, we multiply the magnitude of delta V, which we just found, with the object's mass, which is the mass of the truck, which is 2,100 kilograms. So we can write M equals, the mass of the truck times the change in the truck's velocity, and then take the magnitude of that whole thing. So we can multiply these two terms together, 18.18 meters per second, and then we should get 38,178.5 kilograms meters per second. And that's going to be the magnitude of the change in the truck's momentum. So now we want to find the direction of the change in the truck's momentum. So the direction of the change of the truck's momentum is going to be the same as the direction of the change in the truck's velocity. So if we can find the direction of the change in velocity, we can find the direction of the change in the truck's momentum. So we know that tangent of theta equals opposite over adjacent. Right? So if we call this, let's call this angle right here theta. This angle right here is going to be the exact same as this angle right here. So in this case, the opposite side of theta is going to be Vy, and the adjacent side of theta, the side that's next to theta, that's not the hypotenuse, is going to be Vx. So the opposite side is going to be Vy, and the adjacent side is going to be Vx. So we know that Vy is going to be pointing downwards and it's going to be the same exact magnitude as negative Vi. So Vi is going to be equal to, or rather negative Vi is going to be equal to negative 11.39. And we know that Vf is going to be the exact same as, we know that Vx is going to be the exact same as Vf, the final velocity, which is going to be 14.17. So in this case, to isolate theta, to get theta by itself, we can take the inverse tangent of both sides. And this has the effect of undoing the tangent formula around theta. So by undoing the tangent formula around theta, or the tangent function around theta, we should get theta by itself. So if we take the inverse tangent of both sides, we should get theta by itself, right? So these cancel out. That gives us theta equals the inverse tangent of negative 11.39 over 14.17. And so if you plug that into your calculator, you should get theta is equal to negative 38.8 degrees. And so this is going to be the direction that this vector delta V is pointing, which is also going to give us the direction that the change in momentum delta P is pointing. So therefore, this angle makes sense, right? Because delta V is pointing in the fourth quadrant, right? Since delta V is in the fourth quadrant, so let's imagine that this is a XY coordinate plane. Delta V would be pointing in the fourth quadrant. And the angles that are in the fourth quadrant are going to be between negative 90 degrees and 0 degrees. So because negative 38.8 is in between negative 90 degrees and 0 degrees, this angle makes sense.